You are listening to The Vocal Technologist. Spoken tech for your ears.
You know, usually when we think about building a massive skyscraper, there is this comforting, almost predictable rhythm to it.
Oh, absolutely.
You survey the land, you dig the foundation, you bring in the steel, you pour the concrete. It takes years, right? You can literally watch it rise floor by floor.
Right, because it's a highly visible, highly sequential process. I mean, you can't exactly put the roof on before the framing is done.
Exactly.
And every single step requires human oversight, to ensure the physics actually work out.
Yeah, but imagine you wake up one morning and overnight the construction cranes just, well, they came alive on their own.
That is a terrifying thought.
Right. And not only did they build the next 80 stories while you were sleeping, but they also completely redesigned the architectural blueprints on the fly to, make the building withstand a Category 5 hurricane.
Which just sounds like straight-up science fiction.
It really does. But if you are stepping into the world of software engineering right now, that is exactly what is happening. The cranes have woken up. So today we are doing a deep dive into a really fascinating stack of technology, startup, and programming newsletters from May 21st, 2026.
Yeah, and our mission here is to trace the ripple effects of this massive transition for you. We are moving way past the era where AI was merely this helpful little co-pilot politely suggesting a line of code here and there.
Right, the autocomplete days are over.
Exactly. We are entering the era of fully autonomous agents. These systems are now rewriting the fundamental rules of software architecture, security, and frankly, what it even means to have human expertise.
So I really need your brain to help us connect the dots here, because we are looking at high-level math breakthroughs, major security vulnerabilities, and, well, existential questions about the future of the internet itself.
It is a lot to unpack.
It really is.
Yeah.
So let's start with the math, because this is where I actually had to stop and reread the source twice.
Yeah, it's pretty dense.
The implications are just massive. According to a recent release, an OpenAI reasoning model just became the first autonomous system to solve a major open mathematical problem.
Right.
It disproved Paul Erdő's planar unit distance conjecture from 1946.
Yeah, and to really appreciate why that matters, we have to distinguish between calculation and reasoning.
Okay, break that down for me.
So for decades, computers have been incredible calculators. If you give them a formula, they can crunch a billion numbers in a second.
Sure.
But a conjecture from discrete geometry, like the one Erdő's proposed, it isn't just about crunching numbers. It's asking a fundamental question about the maximum number of pairs of points on a flat plane that can be exactly 1 unit of distance apart.
Oh, I see. So you can't just brute force calculate every possible arrangement of points in infinity.
Exactly, because there's literally no end to the numbers you'd have to check.
Right.
Solving it requires exploring abstract conceptual spaces. It requires identifying novel patterns, forming a hypothesis, testing the logic, and essentially discovering new mathematical truths that no human has ever formalized.
Wow.
The fact that an autonomous system achieved this, it means we have crossed a threshold from mere computation into genuine, sustained logical reasoning. It formed a strategy and followed it through.
Okay, let's unpack this for a second, because sustained strategy is exactly what it takes to build complex software.
Precisely.
And that brings us from abstract math right into the code bases. We have this report about foundation models, specifically looking at one called Qwen 3.7 Max.
Oh yeah, Gwen.
The sources highlight that its defining feature is long horizon execution. What exactly does that mean in practice?
So long horizon execution is basically the bridge between thinking and doing. Traditional AI models are essentially text predictors, right? They just guess the next word based on the previous words.
Right, like an advanced autocomplete?
Exactly, but long horizon execution means the model can hold a complex goal in its mind across thousands of distinct tool calls.
Thousands.
Thousands. It can write a script, run the script, see that it failed, read the error log, write a patch, test it again, and just continue that multi-hour optimization loop without any human prompting at all.
Yeah, it's just wild. And the real-world application of this in our sources is staggering. An AI agent essentially modernized a replicated state library by writing over 130,000 lines of Rust code.
Yep.
It built a new multi-paxos consensus engine. Now, from what I understand, a multi-paxos engine is a notoriously difficult way of keeping distributed servers in sync. Why is that such a massive flex for an AI?
Well, imagine trying to get 50 people in 50 different rooms to agree on a single pizza topping.
Okay, sounds like a nightmare.
It is, but the phone lines keep dropping. Some people are lying, and some people just randomly fall asleep.
Right, yeah.
That is what distributed servers deal with every single second. A multi-Paxos consensus engine requires incredibly precise, fault-tolerant logic to ensure that a network of machines agrees on a single source of truth even when parts of the network are actively failing.
Wow.
It is a notoriously unforgiving architecture. If you get the logic wrong by even 1 microsecond, the data gets corrupted.
And the AI didn't just build it. The source notes it increased the system's throughput from 23,000 operations per second to an incredible 300,000 operations per second.
That's just a massive leap.
So to go back to my skyscraper analogy, this is like hiring an autonomous researcher and architect who successfully executes a year's worth of highly complex structural engineering while you sleep.
That's exactly what it is.
But reading this led me to a much broader realization. If an AI agent can just rewrite 130,000 lines of complex REST code overnight to make a system faster, does the programming language we choose to build our companies on even matter anymore?
You've just hit on one of the most profound shifts in our industry. It is the death of technological lock-in.
The death of lock-in.
Yeah. Historically, choosing a programming language or a framework for a massive enterprise project was a permanent structural trap. If a company chose to build its infrastructure in Java 15 years ago, they were stuck with Java.
Because changing it would be a nightmare.
Right. Paying human engineers to manually translate 1 million lines of code to a more modern, efficient language would literally bankrupt the company in man-hours.
They were effectively held hostage by their original choice.
Yes, absolutely. But agentic programming introduces a world where complex systems can be translated and rewritten rapidly and at an incredibly low cost.
So languages just become completely fungible.
Exactly. They are no longer these permanent concrete foundations. They are just temporary states that an AI can translate in and out of as needed to optimize for whatever your current bottleneck happens to be.
That is incredibly liberating for a business, for sure. But generating 130,000 lines of code at lightning speed introduces a rather severe complication.
Oh, big time.
If you can build infrastructure that fast, you can also generate or exploit vulnerabilities at unprecedented speeds.
It is the ultimate double-edged sword of this revolution. Speed of generation equals speed of vulnerability.
Right, look at the security breaches detailed in our sources. There's the React2 shell flaw.
Yeah, that was a bad one.
A security researcher found a critical remote code execution flaw in React's undocumented flight protocol. The source says they abused complex objects and JavaScript the edibles to hijack the internal workings. Wait, so let me make sure I'm getting the mechanism here.
Go for it.
Because JavaScript is asynchronous, a thornable is basically an IOU, right? It tells the system, hey, run this task and then run this next set of instructions.
That's a good way to put it.
Are the attackers basically tricking the system into accepting a malicious set of instructions by disguising it as one of those routine background then tasks?
That is a perfect way to translate it. They manipulated the pipeline. The system expects a safe, routine data object to process later, but the attacker formats a malicious payload to look exactly like that routine object.
Oh, wow. So when the system eventually executes its background tasks, it unwittingly executes the attacker's code, giving them remote control of the server.
That is terrifying. And the terrifying part is how fast these exploits move. Meta had to confirm the React2 shell flaw in just 17 hours and rush a fix to the entire global community days later.
Just days later. And it isn't just complex web protocols. We also have the GitHub incident in the sources.
Oh, right.
3,800 internal code repositories were compromised simply because a single employee installed a malicious Visual Studio Code extension.
Just one extension.
The attack surface is massive, and one of our sources points out that in languages like C and C++A, essentially everything is undefined behavior.
Yes.
Let's pause on that, because undefined behavior sounds like a minor bug, but it's much worse than that, isn't it?
Oh, far worse. In languages like C and C++A, the language designers prioritized raw speed above all else. To get that speed, they essentially assume the programmer writes perfect code.
Which never happens.
Exactly. If a programmer makes a mistake, like telling the program to read memory that it shouldn't have access to, the language doesn't have a safety net. It doesn't politely stop and give you an error message. It just enters undefined behavior, which means the compiler can do literally whatever it wants. It might crash, it might silently corrupt your data, or it might accidentally create a perfect backdoor for a hacker.
Oh my.
Perfectly correct. C++ code is practically impossible for humans to write at scale because of this.
So the sources suggest we now have to rely on large language models to audit legacy code bases for those subtle flaws. because humans simply cannot perceive the sheer volume of undefined behavior.
Right.
But here's where I really want to push back a bit on this whole ecosystem.
Okay, let's hear it.
If AI is generating code at the speed of light, and the foundational languages we rely on are full of undefined behavior and complex exploit paths, aren't we just accelerating the rate at which we build garbage vulnerable systems?
It's a very fair point.
I mean, if I have an AI write 130,000 lines of code overnight, how do I ever actually trust that it didn't just accidentally invent 1,000 new React 2 shell style vulnerabilities?
That skepticism is entirely justified, and frankly, it is the central anxiety of the agent era right now. We cannot simply rely on building smarter agents and hoping they don't make mistakes.
Right, hope is not a strategy.
Exactly. So the solution highlighted in the engineering community right now is a shift toward a concept called structural back pressure.
Structural back pressure. That sounds like we are building a physical mold or a rigid pipe that the AI's code is forced to flow through, rather than just asking it nicely to write secure code.
That is exactly the mechanism. A source specifically highlights a framework called Shen back pressure. It integrates security invariance directly into the system architecture using a formal specification language. It basically creates deterministic guard types.
Okay, so it's not just a suggestion from a prompt. It's a structural wall the AI cannot pass.
Correct. You are forcing the autonomous agent to repeatedly test and iterate its code against these guard types.
I see.
It's not about hoping the AI is smart enough to avoid a vulnerability. It's about making the environment so rigorously constrained that the AI literally cannot compile or submit code that violates your underlying security logic.
Oh, wow.
Yeah, if it tries to submit code with undefined behavior, the architecture violently rejects it. The architecture pushes back.
I love that concept, the environment pushing back to enforce safety. But this brings up a massive contradiction for me.
Okay.
If the AI is writing the code autonomously,
Right.
and then a different AI system is auditing the code, and structural back pressure is acting as the rigid security guard, what exactly is the human software engineer supposed to do? Are we just the people who turn the servers on and off?
Yeah, this raises a critical question about the nature of expertise itself. One of our sources dives into this fascinating concept called the tacit dimension.
The tacit dimension.
Yeah, it argues that software engineering, and really any high-level craft, relies incredibly heavily on intuitive, unwritten knowledge.
Unwritten knowledge. So like a master baker who knows the dough needs an extra splash of water, not because the recipe says so, but just by feeling the humidity in the kitchen air.
Precisely. That baker possesses tacit knowledge. I can hand you a 50-page manual on the chemical properties of yeast and flour. That is explicit knowledge.
Sure.
But reading that manual will not teach you how the dough is supposed to feel in your hands.
Right, you have to experience it.
Exactly.
Okay.
And in software engineering, there is a deep tacit dimension to understanding how legacy systems interact, or knowing why a particular database architecture will eventually fail under load, even if the math currently looks fine on paper.
And the problem is that AI models are trained exclusively on explicit knowledge. They only know what has been written down in text and code on the internet.
Right. They cannot feel the humidity in the room, to use your analogy. AI cannot grasp the subtle architectural decisions an engineer makes based on 10 years of painful experience if those decisions were never explicitly documented in a README file.
Which ties directly into the insights from Linus Torvalds, the creator of Linux, which our sources mention. He talks about the concept of garbage code.
Yes.
You would naturally think that with AI, we should be writing the most highly abstracted, mathematically complex code possible because, well, the machine can handle it.
That's the assumption, yeah.
But Torvalds argues the exact opposite. He advocates for simple, readable code, even if it means sometimes repeating yourself.
Because he optimizes entirely for the human cognitive load. Modern software engineering often tries to make code clean by hiding the actual logic behind dozens of tiny abstracted helper functions.
Right.
But Torvalds points out, if a developer has to jump across 5 different files just to understand what a single line of code is actually doing, the context switching completely destroys their mental model.
It's like an amateur writer who uses a thesaurus to find the most massive, overly complex vocabulary possible, just to sound smart.
Oh, perfect analogy.
Right, whereas a master novelist just uses simple, direct language that punches you right in the gut. The mastery lives in the simplicity.
Exactly.
But what I found really fascinating in the source is that Torvalds argues this simple, readable code is actually better for the LLMs too.
It is, because just like a human, an AI agent operates better when the logic is linear and transparent. If the AI has to maintain the context of a highly fragmented, abstracted code base, its error rate goes way up.
But are we at risk of losing this human mastery? I mean, if we just let the AI agents do all the heavy lifting, generating thousands of lines of explicit code while we step back, don't we lose that tacit dimension over time?
The tacit dimension source highlights this as an extreme systemic risk. If we over-rely on AI to generate everything, we severely damage the mentorship and apprenticeship pathways in our industry.
Because the juniors have nothing to work on.
Right. Historically, a junior engineer learns that unwritten architectural intuition by sitting next to a senior engineer, struggling through complex logic, and absorbing the why behind a decision.
Yeah.
If AI takes over the explicit writing, how does the next generation acquire the tacit understanding of how to maintain these massive systems when things inevitably break?
We are talking about losing touch with the foundational layers of our code because AI is just abstracting it away.
Exactly.
But we are already seeing what happens when we rely too heavily on centralized abstraction layers in our physical infrastructure. This isn't just theoretical. On May 19, 2026, the deployment platform Railway suffered a massive total outage that lasted for 8 hours.
Yeah, and 8 hours in cloud infrastructure is an absolute eternity.
It's catastrophic for a deployment platform.
Yeah.
And the underlying cause perfectly illustrates the danger of centralization. Railway wasn't hacked. It was an infrastructure cascade failure.
Right.
Google Cloud incorrectly suspended Railway's production account due to an automated administrative error. So wait, how does a billing or administrative suspension take down the actual physical servers running the applications?
Because of centralized dependencies. When the account was suspended, Railway's internal API calls, which verify the system status, they began to fail.
Okay.
And because those APIs were failing, their network route caches couldn't refresh. And when a network cache expires without a refresh, the traffic literally has nowhere to go.
Wow.
The entire system went dark across all regions simply because one centralized abstraction layer, the Google Cloud account status, was flipped off.
It was a single point of failure that brought down their entire ecosystem.
Exactly.
And Railway's solution to this, according to their incident report, is moving to a true mesh network. They are distributing their core dependencies across multiple vendors so that one provider's mistake can't cascade through their entire architecture.
Which is really the only way to build true resilience.
Which brings us to the final piece of our puzzle today. We are looking at a source that discusses Google's transition to AI-generated search results. Now, we want to be very clear for you listening. We are simply relaying the argument made by the author in the source material here.
Right, we aren't endorsing either side.
Exactly. But the author makes a very aggressive claim, calling this a war on the web.
Yeah, the author's argument centers on the mechanics of AI search. Historically, a search engine functioned as a directory, right? It provided direct links to original websites created by human authors.
Right.
The new paradigm uses AI to ingest all that human content and synthesize it into a proprietary, centralized summary right on the search page.
So you don't even need to click anywhere.
Exactly. The author argues that this abstraction layer devalues original human work because users no longer click through to the source. That starves the creators of traffic and revenue, threatening the entire open internet ecosystem.
You know, when you look at the Railway outage, the parallel here is actually striking. Railway realized that relying on a single centralized cloud provider was a catastrophic vulnerability for their physical infrastructure.
Yes.
The author of this search engine piece is essentially arguing that relying on a single centralized AI to summarize the entire internet is a catastrophic vulnerability for our information ecosystem.
It really is the exact same architectural flaw, just applied to a different medium.
True resilience, whether in server architecture or in human knowledge, requires distribution. It requires a mesh network.
If all of our network traffic or all of our code generation or all of our knowledge synthesis is funneled through one or two massive, opaque AI models, we are building the ultimate single point of failure.
Right.
We are shifting from a distributed web of explicit human knowledge to a centralized engine of AI reasoning.
And as we discussed with the tacit dimension, if humans stop building and maintaining the foundational layers, whether that's the code or the original articles on the web, we lose the intuition required to fix the system when that central engine inevitably breaks.
Exactly. We lose the ability to feel the humidity in the room.
Okay, let's take a breath and recap the sheer scale of what we've just covered, because it's a lot.
It is a lot.
We started with the autonomous revolution, AI moving past simple calculation to actually exploring abstract spaces to solve 1946 mathematical conjectures,
Right.
and rewriting 130,000 lines of complex Rust code to manage distributed servers. We saw how this completely destroys the old concept of technological lock-in, making languages entirely fungible.
But we also explored the severe vulnerabilities that speed introduces, like the React 2 shell flaw disguising malicious instructions as background tasks.
Yeah, that was wild.
And that speed necessitates structural backpressure, building rigid architectural molds that physically force the AI to write secure code.
And then we looked at the human counterweight to all this automation, the necessity of simple readable code to reduce cognitive load and the irreplaceable value of tacit knowledge. That unwritten intuitive mastery which AI simply cannot learn from a text file.
Exactly.
Finally, we look at the massive risks of centralization, from Railway's 8-hour cascade outage to the philosophical arguments about AI search engines abstracting away the distributed human web.
Which leaves us with a rather profound paradox to consider based on everything we've read today.
Oh, lay it on us.
If the author of the search engine article is right and AI successfully abstracts away the original human web, if human creators stop publishing explicit text because they no longer get any traffic or recognition, where exactly will the next generation of autonomous AI agents get their training data?
Oh, wow.
Right.
They just run out of source material.
Precisely. Are we currently building an incredibly smart machine that is structurally destined to run out of fuel?
That is the perfect question to leave you with today. If the autonomous cranes are building the skyscraper faster than ever, but they eventually run out of human blueprints to learn from, what happens to the skyline? Thank you so much for joining us on this deep dive. Keep questioning the architecture of the world around you, keep looking for the unwritten rules, and we will catch you next time.
Spoken Tech for your ears.